and kick it off. All right. So hi everyone. Welcome to today's Condensed Matter seminar. My name is Shulei Zhang, the host of today's seminar. It's my great pleasure to introduce our today's speaker, Dr. Ivar Martin from Argonne National Laboratory. Dr. Martin is a condensed matter theorist in the material science division at Argonne National Lab. Dr. Martin got his the Bachelor in Science degree from the Moscow State University and PhD degree from the University of Illinois at Urbana-Champaign. I think you're working with Philip Phillips, right? And in 1999, he went to Los Alamos National Lab, first as a postdoc and then as a staff member there. So in 2013, he joined the Argonne National Lab. So Ivar, research interests include please mute yourself. Ivar's research interests include equilibrium properties of materials, including superconductivity and magnetism, microscopic theory of quantum coherence and quantum measurement, ways to implement usual correlated states in quantum hardware, and the classical nonlinear, as well as classical nonlinear phenomena of phase and mode locking. And recently, he's been particularly interested in ways to create new quantum state by means of strong periodic and quasi-periodic driving. So I think in today's seminar, he's going to tell us about the recent development in this direction. So without further ado, Ivar, please take it away.
Yeah, thank you so much, Shulei. So thank you very much for the invitation, for the introduction. So it's great to be out there, even virtually. Hopefully you guys are not freezing anymore. So here it's getting pretty nice. So the talk today is going to be, in a way, also it's about a virtual world where you can have multiple time dimensions. Of course, like the real world that we live in, as far as we know, has just one time dimension, and it's sort of the time is moving only one way. But it turns out that if you consider driven systems, and by driven I mean, say, you apply either periodic drive or maybe multiple periodic drives, making the drive quasi-periodic, you can actually create effectively multiple time dimensions. And as you do, you can actually start also using them in a way similar to the way we use real space dimensions. You can build lattices, you can study various phenomena, but those phenomena are going to be of a different flavor because they reside in time rather than in space. So let me mention right away my collaborators on this work, and primarily we started collaborating and we still are with Gil Rafael from Caltech, and at various stages also worked with Bert Halperin, Frederick Nathan, Mark Rodner, Anusha Chandran, and Phil Crowley. And as we go along, I'm going to mention specifically the works, related works with these people. Okay, so the fact that time can play a role of extra dimension actually is not something particularly strange, and in fact, it's not even necessarily associated with quantum systems. In fact, something quite similar happens in classical systems. So let me give you an example. So this is the famous system of equations which describes the Lorentz attractor, and so it's a dynamical system. So it's basically an evolution in three-dimensional space, x, y, and z. And this evolution is happening as a function of time. So these equations, they were constructed by Lorentz in order to try to make sense of, I guess, weather patterns. And that's a classic system used to illustrate the concept of chaos. So it's kind of like a minimal system in the sense that you need at least three-dimensional space in order to get chaos. Plus, you need nonlinearity. And here you see that the dimensions x and z, for example, interact, and dimensions x and y interact. And as a result, you get this interesting situation where the evolution is completely deterministic. So let's say you start here and you keep moving and you end up somewhere there after a long time. But even tiny perturbation in the initial conditions will lead to very different evolution down the line. And in fact, the divergence of trajectories can be exponential, and the exponent of this divergence is called Lyapunov exponent. Curiously enough, if you go to fewer dimensional spaces, so two-dimensional space, x and y, yeah, it doesn't really matter what you put on the right-hand side in the evolution equations. There is no way to get chaos. The space is just too simple. Two-dimensional space is just too simple to get any exponentially divergent trajectories. So you either get cycles or you get saddle points. That's pretty much it. So this goes by the name of, at least that's one of the statements of Poincaré-Bendixsen's theorem. However, if I introduce drive, even some simplest drive like this, somewhere in the evolution equations, making them explicitly time dependent, and then the situation can change. And so one way to make sense of this is to realize that this system of equations actually I can rewrite as a system with time independent right-hand side. Definitely it was a bit of nonlinearity, but now with one extra dimension, and this extra dimension is nothing but the phase of the drive, and the time evolution of the phase and the rate of evolution is given by the frequency omega. Okay, so what it shows is that adding a drive does at least superficially look like an extra dimension, and since you have now three-dimensional phase space, indeed you'd expect that there could be some non-trivial behavior. And okay, so let me just clarify this a little bit, because last time I was giving this talk, there was a bit of a confusion here. So here we have, it's important to state that on the left-hand side, we have first-order derivatives. So let's say with two equations, I only need to specify two initial conditions, the initial x and initial y, and then I can predict the whole evolution. If I have a driven system, I need to know the initial x, initial y, and initial phase of the drive. And then I can predict the full evolution just by integrating these equations. So that's the meaning of the statement that the phase space is three-dimensional. So, and it's slightly confusing because we have this phase and there's a phase in more general sense of like, say different coordinates or coordinates momenta and so on and so forth. Okay, so by now you're probably sort of semi-convinced that, okay, so maybe it will be more interesting. And indeed, there are lots of examples where you can take a simple system, which nominally has just two-dimensional phase space, you start driving it, and then suddenly it becomes much more interesting. It can start exhibiting bifurcations, it can start exhibiting various phase-locked states, and that's an example of a driven nonlinear oscillator, which is effectively two-dimensional because its phase space is the coordinate and momentum, or coordinate and velocity, in the presence of a drive, and then as a function of drive period and the drive strength, you get all this multiplicity of interesting behaviors which are commonly associated with possibility of chaos. Okay, so and I guess the interpretation that I want to pitch is that, okay, it is really because you introduced an extra dimension. In fact, if you added more drives with other frequencies, then effectively your phase space would expand even further, because now you'd need to specify not only phase of this drive, but you would need to specify also initial phases for all the drives that you're applying if the frequencies are incommensurate. Okay, so that's classical story. So the bulk of the talk actually is going to be about the quantum systems. And what I'm going to show you is that for quantum systems as well, time, if you think in terms of Hamiltonians, time can naturally become a synthetic dimension. And in fact, for periodically driven systems, it's as if you're creating an extra lattice, almost like a tight binding lattice in the frequency space. And if you apply multiple drives, which are incommensurate, then effectively you're creating multiple extra dimensions. Okay, so what's what are those dimensions good for? I'm going to show you. I'm going to focus on just one example in this talk. I'm going to show you how to create an analog of a topological insulator purely in time domain. So we'll basically get rid of spatial dimensions altogether, and we'll create a topological insulator in time domain, which will correspond to a system which is being pumped, in this case, by two drives, two coherent monochromatic drives. And this topological conductance, or sort of the analog of the quantized Hall conductance in this case, will be the quantized energy pumping. So the rate of energy pumping, or the power of the energy pumping, is going to be basically determined by the same properties as the Hall conductance is determined in the canonical quantum Hall systems, or Chern insulators and such. So this I'll demonstrate with just classical drives, coherent drives applied to the system, but I'll also show you that these are these constraints are not very strong, and in fact you can replace a classical drive by a cavity, and you still get the same phenomenon, essentially, that you can achieve pumping, and in this case, for instance, you can have just single drive on, and the cavity providing you sort of a resonator into which the energy can be pumped, which potentially could make it interesting, because it could allow you to transform, any incoming frequency into some other outgoing frequency of your liking, and this would be, as I'll show you, a strongly nonlinear effect, which is not a usual, like Chi2, Chi3 type of wave mixing that we are more familiar with. And so in fact, the cavity would also introduce degrees of freedom. And in this case, I'll show you that, in fact, various behaviors that one can obtain can be either chaotic or can be regular, and they correspond to different regimes. Okay, so let us start. So time as a synthetic dimension. Okay, somehow it's a bit slow. Okay, yeah. So suppose you have a quantum system which is described by the Hamiltonian, which has a static part, time-independent part, H0, and it has a time-periodic part. And so basically H0 and B are some operators in the Hilbert space of the system. So for instance, if you're driving a two-level system, then these would be some 2x2 matrices. If you're driving n-level system, it will be some n-by-n Hermitian matrices. Okay, so of course, this is not the most general Hamiltonian you can have that has a drive in it, but it's good enough for our illustrative purposes. Okay, so the solution of the Schrodinger equation, which is basically, time derivative of psi is equal to h times psi, we can search for in the following form. Okay, we can say that the general time-dependent wave function is can be effectively expanded in terms of harmonics. So there is a slight caveat that many of you probably will notice, but let me just say it like this: that out of the full time-dependent wave function, I'm going to extract bits which have oscillatory components in it, and the rest. Okay, and so basically the psi n is going to be the time-dependent coefficient of the exponential which oscillates with the frequency and omega. Okay, so you'll notice that that's not a kind of like standard Fourier expansion, because in the Fourier expansion you would just say that I have a periodic function and I'm expanding it in terms of harmonics, and then this guy would be time independent. So there is a bit more content hidden in this expression. In fact, it follows from the Flequet theorem that session expansion makes sense, and also what is the meaning of these guys. But for the purposes of what I'm going to show you, it's enough to think that this is an ansatz. So let's look for a solution of the Schrödinger equation in this particular form. Okay, so now we stick into the Schrödinger equation, and we're going to collect the like terms, right? We're going to collect the terms which has e to power I n omega t. So that's going to be sort of one row or one equation, and we're going to do it for all different n's. So now you can see immediately that since h naught doesn't have any time dependence in it, the time derivative of this psi n is going to be connected to the same psi n by the Hamiltonian h naught. However, these guys, the drive terms, they kind of like they up the frequency or decrease the frequency, and therefore these guys begin to act kind of like hopping operators in this effective n lattice. So the v terms are going to connect the n plus 1 and n minus 1. Okay, and here it's just the basic algebra, right? I mean, we just substitute into the time-dependent Schrödinger equation, and we collect the terms which have the same exponential factors. Okay, so but then there's another bit which comes from the time derivative hitting the exponential itself, and let's move it over to the right-hand side, and then you'll see that there is an extra bit which is generated, this omega n times psi n. Okay. Okay, so we have our system of Schrödinger equations, and now let's think what it means. So this looks probably to many of you extremely familiar. So it looks like a Schrödinger equation on a tight binding lattice. All right, so you have some amplitude to be on site 10, and so you can either stay on the same site with the on-site Hamiltonian, or you can hop between different n sites. Okay, and so what is this n? So n is really, okay, it came from this time dependence, but you can think of it as a Green's function, if you like, of a multi-photon state, right? So if I have, I would say, n photons occupying the mode with frequency omega, that's how those n photons gonna evolve. So essentially, without explicitly saying so, this n counts the sort of the position in the Hilbert space of the photons, so to speak. Or put simply, it counts how many photons are being absorbed or emitted due to the interaction with the system. Okay. So graphically we can represent it like this. So we have a lattice. The lattice sites are labeled by the number of photons, say, absorbed or emitted. Now this matrix element V basically takes us between neighboring sites, and so that's our graphical representation of Hamiltonian. But now, yeah, the curious thing is that in addition to the hopping, we also have generated this other bit, and this other is basically like an electric field, because it's a potential which is linearly changing with the position so we really have an analog of a kind of Wannier start ladder, right, where we tilted the potential, and as a result, you expect, for example, in the lattice problems, you expect to get some oscillations where the wave packet sort of moves back and forth in the presence of electric field. So the motion becomes, in fact, confined in the direction of the field.
So I just wanted to make sure I'm following. So if you had a two-level system, then you're saying you can unfold it into a lattice, and there's a two-component wave function at every side. Is that right?
Precisely. Yeah.
Okay. Yeah. Good.
Exactly. And the confinement comes about because your spectrum of the two-level system is bounded, so you cannot bump infinite amount of energy into it. So it can jump on this lattice only that far, and then it will have to bounce back. So that's the reason for this localization. Yeah. All right. So that's kind of cute, right? So it already can give you a little bit of intuition for what might be happening in the system. What's interesting is that you can generalize this to more than one drive. So say now we have drive with frequency omega-1 and drive with frequency omega-2. And for the sake of argument, let's say that the frequencies are incommensurate. So omega-1 over omega-2 is not equal to a ratio of integers. Okay, and now let's try to go through with the same procedure as before. So we're going to think of it as an ansatz. We're going to take a different kind of ansatz this time around. So it's going to contain sort of both harmonics, both frequencies. And so now I'm going to label this the coefficient of each one of those harmonics, so to speak, with two labels, N1 and N2. And now, why does it make sense? Because if omega-1 or omega-2 are incommensurate, there are no two combinations of N1 and N2 that are going to give me the same combined phase factor. So essentially, each one of those phase factors labeled by N1 and N2 is going to have its own unique amplitude. Okay, so now we just go ahead and stick it into Schrödinger equation, precisely same as before. But now, in addition to what we had in the previous case, we have this hopping in the second direction. So you can think of this as hopping in the x direction, while this will be like hopping in the orthogonal, say, y direction. That's one difference. And the other difference is that now by hitting this phase factor with the time derivative, we actually generate a linear combination of omega-1 and omega-2. And if you think about it, it still looks like an electric field, right? It's just that this electric field now is pointing in some direction. In fact, if omega-1 is not commensurate with omega-2, this direction is going to be non-crystallographic. So it's an electric field pointing in some direction relative to the crystal axis. But nevertheless, it's still some sort of a Wannier-Stark type of problem, but now in 2 dimensions. And you can already see that, yeah, you can keep going. You can add more frequencies, and this way you expand your space even more and more. So you can anticipate that the dynamics is going to be clearly more rich, but also it seems like we can glean some understanding from this sort of analogy to the lattices, because particularly if you're in the solid state business, I mean, you see these lattices days in and days out, so they're painfully familiar. Okay, now so to and then follow along with this idea of confinement. So if we have a lattice and the kind of like local Hamiltonian has a scale, so the spectrum is bounded, then again, just like in the 1D case, you cannot really move too far in the direction of electric fields. You run out of bandwidth and you'll have to bounce back. So it's kind of like, again, those Bloch oscillations. But you also have an orthogonal direction in this case when you have more than one dimensional system and more than one drive. And so this direction is actually free in the sense that you can move in this direction without really changing the energy. So this is kind of like deconfined direction, so to speak. So that's the difference. And the condition for, if you think about it, for this direction is that the product of omega-1 and 1 plus omega-2 and 2 has to remain roughly constant. And this, again, you can very naturally interpret as the sort of total amount of energy that you absorb from the drive 1 and the total amount of energy that you absorb from the drive 2. Altogether, they have to add up to a constant. Okay. Okay, so here's, let me mention one more thing here. So the color of these dots here is significant. And what it's supposed to represent is the following. So the situation when the frequencies are incommensurate corresponds to the case where, in fact, all those lattice sites are unique. So you really need to specify this wave function on all the sites separately. However, the picture is still quite useful even if the frequencies omega-1 and omega-2 are commensurate. It's just that you don't have the full two-dimensional space. The space of unique possibilities or unique sites n1 and 2 becomes limited. So instead of being a full 2D plane, it becomes a cylinder. So you'll have to identify, let's say, this boundary with that boundary of the of this red strip. So it becomes a cylinder, and in this case, this is drawn for incommensuration. Well, for commensuration 3:2. So the ratio of the frequencies is 1.5. And you can see that, like if you use the analogy from the quantum hole and so on, the difference between cylinders or tori and flat spaces is not so huge if, for instance, your the circumference has many sites in it, or let's say if your magnetic length is smaller than the perimeter. So you can sort of already foresee that, in fact, commensurate and incommensurate cases are not going to be that hugely different at the qualitative level. They're going to be quite similar unless the commensuration is some super trivial, say 1:2. Okay. Okay. So now let's see what this could be useful for. Okay. So first, let me remind you, give you. Actually, let me move this thing. I have this bar floating. The zoom bar. Yeah. Okay. So yeah, let me remind you how the things work in spatial dimensions. How do we get interesting topological insulators in space? Okay, and that's something that people have been actively working on maybe for the past 15, 16 years now, ever since sort of spintronics, anomalous Hall effects, and so on, and quantized topological insulators. And of course, the prehistory goes even deeper into the 80s, into integer Hall effect. But so we'll focus on the sort of more recent sort of incarnation of this physics. So the fruit fly of the topological band structures perhaps could be considered to be the BHZ model, the Bernoulli-Hughes-Zhang model. And so this is a tight binding lattice. It's two-dimensional square lattice. It has two bands, so which is sort of bare minimum to get anything interesting topological. So here, the Pauli matrices, they correspond to the bands. And K1 is like momentum in the x direction, K2 is momentum in the y direction. So this model has a few parameters, and depending on these parameters, so the model either becomes topological or non-topological. And I'll explain the meaning of that. So in particular, this term is called mass. And if the mass is too large, then it becomes trivial. If it's within some bounds, then the model is non-trivial. Now, so how does this sort of BHZ magic works? So geometrically, you can understand it very simply by realizing that this Hamiltonian is basically a dot product of the vector of Pauli matrices and some vector, again, 3 vector, which depends on kx and ky. Okay, and this n is going to be the unit vector in the direction of d. Also clearly, if you diagonalize this Hamiltonian, you'll realize that the energy states, the energies of these states are given by the length of d, and the gap is basically twice d, because essentially it's like a spin in a magnetic field. It's just that this magnetic field is a function of momentum. So now, if the gap is full, then this vector n is well defined. So if the gap doesn't turn into 0 anywhere inside the Brillouin zone, so then n hat is well defined everywhere. And if it is, we can calculate this kind of object. We can calculate this whole conductivity. And the Cooper formula essentially leads to the following expression, that the whole conductivity is double integral over the Brillouin zone of the triple product of n with its derivatives with respect to kx and ky. So the cute thing is that, as we know from the quantum Hall effects, is that this expression cannot take arbitrary values if the system is an insulator. It can only take quantized values. And the reason for that is that this expression actually counts the sort of the wrapping number or the churn number, which corresponds to the mapping from the momentum space into the space of this n vector, which is a unit sphere. And for instance, if let's say this is our upper band, this is our lower band, and if it so happens that the vector n shown here by this bluish arrow starts, let's say, pointing up and near the almost band touching, and points down eventually as we go sufficiently far away. So then that would precisely correspond to mapping. So let's say this would be the North Pole here, and so let's say this periphery far away would correspond to the South Pole. And this way we can, for example, here have a wrapping number of 1, which would correspond to monopole conductivity of E squared over H. Okay. So it has very simple sort of geometric meaning at the level of Hamiltonian for what's happening. And again, depending on the parameters, the wrapping can be either complete or incomplete, and that's how you get topologically trivial, which is sigma xy equal to 0, or topologically non-trivial regimes where sigma xy is quantized to non-zero. Okay. So the phase diagram, it will be useful for the future. So let me show you sort of a couple of ways to slice it. So suppose we fix B1 and B2, so these guys to be equal to each other, and then what you can see is that if the mass is too large, then we end up with the trivial regime because we're dominated by this by the sigma z term, and the k dependence is more or less irrelevant, and we don't really wrap the full sphere. And if the M is not too large, then we can either get churn number 1 or -1. Okay, so that's one possibility. And the sign of the churn number is determined also by the signs of B1, B2, and in fact also B1, B2. All right, so the other way to slice it is to fix the mass and see what happens as we change B1 and B2. and there's a clear correspondence. So if I go this way and this way in this phase diagram, but the gist of it is that B1 and B2 have to be simultaneously pretty large in order to be in topological regime. The only exception is like these points where, in fact, only one of the B's has to be pretty large, but the other can be pretty small, and we still can be in a topological phase. Okay, any questions at this point?
Sorry,
Yeah.
I had a quick question.
Uh-huh.
In the previous slide. So, I mean, the assumption is that at negative infinity, the arrows point downward, right?
Yeah. So if you have a system which is continuum, so there your k's are not bounded, you would say that's if at infinity all points down, then you're good. In reality, if you are talking about lattice systems, you naturally have a cutoff, right? You live in a Brillouin zone, which is a torus in 2D, and then you just literally have to count the full mapping between the torus and a sphere. And again, this one is also classified by this wrapping number. Okay.
Thank you.
Any other questions? Okay. All right then. Okay, so that's how it looks in real space, right? Now, okay, this is kind of nice, right? It's a very geometric way to think about it, but perhaps it's not super intuitive, like why this corresponds to quantized Hall effect. And for that, actually, people have developed a very useful way to think about it. And what one can do, one can analyze the semi-classical equations of motion. And it turns out that the fact that there is a Chern number corresponds to precisely having a magnetic field, but effectively not in real space, but in the momentum space. Okay, and so let me show you quickly how that goes. So one can introduce a so-called a Berry connection, which is a derivative over momentum, or rather expectation value of this momentum gradient over the wave functions, over the Bloch wave functions, the size of k. And there are some subtleties. There's gauge freedom associated with that because you can obviously choose the phase of these guys any way you like. But it turns out that this gauge freedom only affects A, but it doesn't affect, just like with usual vector potentials and magnetic fields, it does not affect the curl of A. And this curl of A, called various different things, in particular Berry curvature, is the field which plays the role analogous to magnetic field that we are very familiar with in real space. So in particular, if we write down the equation of motion for the center of the wave packets, it's given by obviously the first part is just the group velocity, but then there's this extra bit, which is the Berry curvature crossed with the velocity, but this velocity is in the momentum space, not in real space. So the real space velocity will be dr dt, but here we have dk dt. Okay, so this becomes our sort of constitutive equation of motion for the wave packets in the presence of Berry curvature. Now, and I should mention that the integral of Berry curvature is precisely the Chern number. Okay, so how does it look now for this wave packet? So suppose we create a wave packet which is localized both in the momentum space and in the real space. So it's a nice, say, Gaussian wave packet. And we apply an electric field in the x direction. So under this electric field, k begins to rise, to increase linearly. And if we analyze then what's going to happen with the real space position of the wave packet, you will see that as we go across the Brillouin zone and we land essentially at the same point, right, because these points are identified, the wave packet in real space can actually drift off in a particular direction, and this direction is going to be governed by the magnetic field that it has encountered in the momentum space. Okay, so it's kind of like this. So that's ultimately the reason for this Hall effect. So the usual Hall effect is because of the magnetic field in real space, but this Hall effect is because of the effective magnetic fields in the momentum space. Okay. So here we looked at the sort of churn insulators from a couple of different perspectives. Now let's transcribe it into the time-dependent problem. Okay. So for the time-dependent problems, actually, it turns out that you don't really need to do too much. We pretty much done. The only thing we need to do is to make the following substitution. So we can replace the momentum with the phase of the drive. Okay. So where we had k1, k2, now we're going to have omega1 t and omega2 t, and the phi's are just you can think of them as the initial phases of those drives. Okay, so that's going to be our working Hamiltonian, and so based on what I told you, you could expect that there's going to be something topological associated with this Hamiltonian as well, because remember these sines of k1 and cosines of k1 and k2 they correspond to hopping on the real space lattice, but now these guys they're going to introduce hopping, or they correspond to the hopping on the frequency lattice. So we're really going to swap out the real space now for the frequency space, and we want to see what's going to be the physics associated with this. But yeah, at the most basic level, now what we have is just a spin half particle object, which is interacting with some magnetic fields, and so we have magnetic fields pointing both in all directions, in x, y, and z. And if you think about it, the omega1 field is hitting x and z, so it's some sort of elliptical lights in the xz plane, and omega2 is hitting sigma y and sigma z, so it's also some sort of elliptical light in the yz plane. Okay, and the m guy is just a static magnetic field in the z direction. So that's all we have. So it seems like a pretty basic NMR type of setup. So you would have thought perhaps, okay, so that's what could be unknown about it. Yeah, so this is basically how it looks like. So we have a spin which is subjected to a couple of drives. But now we're going to sort of think about this problem again in this in the frequency lattice terms, and we're going to try to figure out what's going to happen to it. So the convenient way to analyze it again is to think immediately in terms of the semi-classics. Okay, so we have our Hamiltonian. As I showed you, we can construct the vector potential and the Berry curvatures, but now we're going to do it in the phase space as opposed to momentum space. So we replace the k1 and k2 by the by the phases of the corresponding drives. So basically, dk dt becomes omega. But other than that, really, there isn't much that you need to change. Okay, so we still have the same semi-classical equation of motion, except that now you should think of this R not as position in real space, but rather position within this frequency lattice. And you see that if there is some sort of Berry curvature associated with this model, then there will be some effective drift, Hall-like drift present in the system as well. And then okay, so so this is perhaps the non-trivial part. That in the quantum Hall systems, we know that the transverse current is basically quantized in proportion to the electric field. So the whole conductivity is quantized. So similarly, we can hope that there will be a current in the frequency lattice, which is also quantized with the average Berry curvature that we encounter, because we're sampling through the system. And the non-trivial part is that the correspondence between the average Berry curvature and the Chern number is actually not guaranteed here, unlike the quantum Hall effect, where it's basically just a statement of the fact that you have a full band, valence band occupied, so you sum over all the brilliant zones, so you're done. So here we're looking at a time-dependent problem, so we don't have a filled band of particles. So this is something which we then still have to justify. But perhaps some of you already see why this will be the case. Okay. So, but okay, I'll show you in a minute, sort of to keep the suspense a bit longer. But but if this thing is correct, then of course this the current in the position in the n, I just redrawing it here, can be converted into the energy current, which is basically the pumping rate, by multiplying this either n1 or n2 by n-1 or n-2. And then you see that this expression becomes simply the average Berry curvature times the product of frequencies, which you can also think of as basically pumping energy of a photon of color 1 during the time period of color 2, of pump 2. Okay, so that's what we kind of anticipate, and again, geometrically, it would correspond to basically moving on this lattice in the direction transverse to the effective electric field, which is the vector of frequencies. Okay, so I realize this may be a bit confusing, so please ask questions if you have any. Okay, so this may sound plausible. Hopefully, it sounds plausible, but but probably you would want to actually understand it in a bit more detail. And luckily, the problem is simple enough that you can, if not analytically, you can easily solve it numerically. So the Hamiltonian that we have is basically a sum of two terms, one coming from the drive 1 and the other coming from the drive 2. And what we want to calculate is basically the rate of change of, let's say, the first Hamiltonian with respect to time. And so here the psi is basically the time evolved wave function, which luckily we can calculate straightforwardly, because say if we're dealing with a some simple system like spin half, we just have two levels. It's very easy to directly integrate these kind of systems forward in time. Okay, so this is like time ordered exponential. Okay, so now the important thing is that something which I haven't emphasized very much, but it is quite critical, is that this mapping onto lattice is only useful if the drive is reasonably slow, right? And what does that mean? It has to be in the energy units, the frequency of the drive, or frequency of or energy of the photons, has to be smaller than the energy scale of the lattice, because only in this case you will be able to sort of really see this as a lattice on which you can hop some reasonable distance and not just be localized, say on a particular site. And because if the photon is at super high frequency, then you really cannot absorb photons, you cannot emit photons. There is just no such energy in your system that would allow you to do that. Okay, so but yeah, if this condition holds, then actually the wave functions are expected to be spread out a bit, So you can think of this as the range of the Bloch oscillations, how far the wave packets would travel back and forth. So if you think in terms of the driven systems, you want to be in a regime which is almost adiabatical. So the drive is very strong and not very fast. The frequency is not very fast. Okay, so let me show you examples. So since we started with incommensurate frequencies, let me do just that. Let me take let's say frequency of the first drive, which is 1/10, and 1/10 of watts. So that's kind of like the scale of the Hamiltonian. And picking it at 110 means that the frequency is indeed slow compared to the scale of Hamiltonian. And the second frequency is going to be the first frequency times the golden mean, which is as irrational as they get. Okay, so now, so here's the critical point. So suppose we initialized our system in some states, and our Hamiltonian at the initial time had the phase of drive 1, which was this, and phase of drive 2, which was like in this picture, it would be 0, right? Because position within this Brillouin zone is really the phases of the drives. But now, as a function of time, the phase is going to start ramping up, both the phase of first drive and the phase of the second drive. And it goes this way, then because of periodic boundary conditions, it shows up over here, then it shows up again over there. And now you see where this incommensurability matters, because so within this Brillouin zone, we basically keep scanning different regions of this Brillouin zone. And because the frequencies are incommensurate, we're going to cover uniformly the whole Brillouin zone. And as a result, indeed, the average Berry curvature that our system sees is going to be proportional to the integral of the Berry curvature, which, as you remember, is basically the Chern number. So this is the reason that this driven system, in fact, will behave like a quantum Hall insulator, but in the frequency space, because it samples the whole Brillouin zone over time, even though we don't have, like in the usual insulators, we don't have a bunch of particles sitting at each individual location in the Brillouin zone. Okay, so that's the resolution of that sort of puzzle. Okay, so but literally you can just go and calculate and see, let's see how the energy in the first drive and the second drive changes as a function of time. And you see that's indeed, you see that those energies change linearly. Let's say increase in one drive and decrease in the second drive. And if I change parameters of the model, sorry, if I change the mass term, which is this constant magnetic field, that really doesn't do anything to the slope. The only thing, it sort of changes the amount of this sort of fuzz. And this is also understandable. Now, the boundary between the topological and non-topological is happening at m equal to 2. And you see that's when m is like 1.8, you already see that stuff sort of begins to deteriorate. And when we go to the non-topological regime, then there's basically no pumping. So this is really the manifestation of the quantum Hall behavior in this system. And so there is this concept of fidelity that we can introduce, which basically effectively just tracks how adiabatically the system behaves, like how well the spin is tracking the instantaneous magnetic field. And for the pumping to occur, it has to track pretty well. If it ceases tracking, sort of falls out of registry with the magnetic field, then the pumping goes away. And in the non-topological regime, I mean, it can be adiabatic, you can track, but you still get no power. So the power collapses as you exit the topological regime. Okay, any questions here?
Yeah, sorry, I had a quick question. So just to clarify, you're getting non-trivial topology because the frequencies are incommensurate?
No. So the non-trivial topology really would happen for any incommensurate frequencies. But whether you're, let's say, so if you look at this picture, right? So the profile of the Berry curvature is only determined by the master and by the B's and perhaps also by the V's, basically by the parameters of the Hamiltonian outside the phase. So the phase or the frequencies, they only tell you like how you sample this Brillouin zone. So for example, this slope is the golden mean. If you pick the ratio of frequencies to be something else, let's say 1 over golden mean, then it would be going sort of more slowly, but you can in principle pick any irrational and you guarantee that you're going to sample the whole, this whole Brillouin zone, this whole square, okay? But if I took rational, and so that's going to be the next example. So let me just go here. But I don't have the Brillouin zone, unfortunately, here. Okay, let me jump back. If I took the rational ratio of omega 1 and omega 2, then after, what is this called? Like least common multiplier or multiple. After a certain number of cycles, you would come back to exactly the same point in this trajectory. And so what it means is that you will have sampled the Brillouin zone with to some degree, but fairly coarsely. And therefore, you don't really expect that will approximate the integral of Berry curvature. It will be deviating a bit. Mm-hmm.
Thank you.
Yeah,
so conversely, if you were doing the rational case, even if you don't have even if the Chern number is 0, you might see an effect.
Precisely.
Because,
Exactly. Yeah, that's sort of the counterpoint. Yeah, precisely.
Yeah, actually, I had a quick question. Now that we've interrupted you, your analysis, is it restricted to the? So initially, when you wrote down that ansatz, I was hoping that you might go beyond the adiabatic approximation, but you're saying that you can't do that because the electric field you create is too strong if you go non-adiabatic. Is that right?
That's right. So, and we were also like in the work with Anusha and Phil Crawley, we were hoping that there is an actual transition, like as a function of frequency, but okay, okay, the pleasures of working from home. Let me kick them out just one second.
That's fine. Yeah.
Okay. Yeah, I guess they realized that I need help with your question. Right. So it turns out that for regular models like this, which are not fine-tuned, basically any finite frequency eventually is going to kick you out of the adiabatic regime. So you can think of this in the band picture. So suppose you have two bands, and it could be just again like a real space insulator, and now you apply electric field. So there will be for arbitrarily electric field, of course, there will be eventually dielectric breakdown, because you're going to go through those Landau-Zener transitions, and if you do it sufficient number of times, it's going to break down. However, it is exponentially slow, right, in the rate. So the rate goes into the denominator. So it turns out that you can do scalings of various sorts, and that's what we try to do with Anusha and Phil. And indeed, you can see curious things. For instance, you can even capture the sort of half integer Hall effects when you have Dirac touching. So when the gap even goes into 0. So if you look at this thing in a particular way, you can even sort of tease out the half quantized resistivity. So yes, there are ways to go beyond adiabatic, but they're kind of tricky. Well, the other one would be to add so-called counter diabatic terms, which actually eliminate the non-adiabatic transitions, and then you get perfect quantization forever.
Right.
Yeah.
Nice. Thanks.
Mm-hmm. Okay, yeah, so from the spin's perspective, just to quickly show it to you. So those different regimes correspond to either like being able to cover fully the Bloch sphere or sort of the spin sphere, or if you're in the non-topological regime, you just sort of land end up covering just a fraction of the sphere. So it has very sort of simple geometric meaning to it as well. Okay, so this is, okay, so let me just very quickly flash this. So if the frequencies are rationally related, in fact, it was very small P and Q, just 3 to 2, you still get the pumping. And in fact, as Harsh mentioned, like even if you're outside the topological regime, so here M2.2 nominally should be already outside the topological regime. But because you're sampling only subsection of the Brillouin zone, or like only like measure 0 of the Brillouin zone, in fact, the pumping can be quite strong. In fact, could be stronger even than the quantized value. Okay, so that's where kind of like the classical drive story ends. And what we wanted to see, and that's the work was that involves heavily Frederick Nathan. We wanted to see, okay, so what if we replace one of the drives by a cavity? Because that would be kind of an interesting situation, right? Where you just have an empty cavity, you have this nonlinear system sitting in there, and you drive it externally with single tone, but you generate at the output whatever you want, whatever frequency you want, just by tuning the resonance of the cavity, say geometrically. And indeed, it turns out that it works. And in the process, you generate some interesting non-classical states of the cavity and spin. You can, in fact, reach the pumping states starting from the vacuum inside the cavity. And you get interesting phase locking phenomena. And it turns out that, in fact, adding dissipation, dephasing doesn't really kill the effect. It's still can be quite robust, or in fact, it is quite robust. So I realize that the time is pretty short. So if you give me maybe 5 minutes, I'm gonna try to wrap up. Is that all right?
That's all right. That's all right.
Okay. So okay. So what is this quantum cavity? So we start from the model as before. So these are classical drives. But now let's replace one of the drives with a cavity. And what it means is that's kind of like replace one quadrature, say sine by momentum, and cosine by position of an oscillator, right? So this will be, and then like A dagger minus A, and this will be A dagger plus A, where A's are just creation annihilation operators for the for the boson. And now the boson itself is going to have its own Hamiltonian with frequency omega-2. Okay, so physically it's this kind of situation. We have single drive, two-level system, and then we have some mode structure inside the cavity. Okay, going back to the phase diagram, that's what I showed you before. So that was like amplitude of second drive. This was the amplitude of the first drive. But now it's going to be also convenient to think in terms of the occupation number inside the, let's say, second cavity. So that's the guy that we are going to quantize. And B1 is still going to be, for now, our classical drive. So the thing to notice here, which I think particularly interesting, is that you can start with empty second cavity, N2, but you can still be at the border of the topological regime, right? So in fact, you can anticipate that there will be some sort of instability, even in this case. That's kind of like what we hope for. But if we start somewhere away, if the drive of the, let's say, the drive sort of counterintuitively is stronger than the sweet spot, then in fact, you don't anticipate that starting with the empty cavity will lead into some sort of interesting pumping regime, because here you're trivial. Okay, so let's see if it pans out. So let's do first the sort of the less interesting case. So here we actually have to start with the cavity populated in order to enter the pumping regime. So these straight white lines are the boundaries of the pumping regime. And you see that as soon as we turn on the drive, there is a drift in the occupation number of the cavity. So that's this N2. And this is time. As a function of time, it sort of starts decreasing. It hits the boundary of topological regime. It flips. and the n begins to increase, and then some fuzz occurs. So the wave function, which is represented here, is actually fairly complex. You see, it's pretty complicated. So this would be like a wave packet Gaussian state, but so this progressively gets pretty hairy. But you see that the rate of the rate of change in the occupation number is in fact consistent with our theoretical expectation. So it still works nicely. Now, yeah, okay. So the sort of the cuter example is if we start with a drive strength precisely at the sweet spot, and then we see that indeed we can start with empty cavity, so being in the vacuum state to begin with. But then as a function of time, the occupation number begins to increase and then decreases, and so again, it sort of bounces between the topological, non-topological boundaries, except that now one of the boundaries is sitting at zero occupancy of the cavity. So, and this is kind of like, yeah, that's the, I mean, if there is anything potentially useful here, probably that's this, that you can, yeah, just have single source, single drive, empty cavity, and then you start populating this cavity with the photons that you like. Okay, so there are also other regimes that I'm just briefly going to mention, which you could have expected if you were expert in like nonlinear dynamical systems, and these are sort of analogs of the phase locking effects, but for quantum system to begin with. So it turns out that you can get like a period tripling phenomena. So if you look at the spectral function of what's happening in the cavity, you'll see that you get peaks at the 1/3 of the drive frequency, and if you drive at different frequencies, then you get other fractions, and so on. So in dynamical systems, it's a very well-known phenomenon. In quantum systems, seems like much less so. But yeah, that's one example how this can happen, and it turns out that it also has interesting connections with time crystals, and probably many of you have thought about them, certainly have heard about them, and yeah, I can tell you later if there's interest how that works. But it has all those hallmarks of time crystallinity that if you look at the quasi energies, there is like spectral pairing, or in this case tripling, that multiple states have very small quasi energy splitting if you plot them right, and there are lots of those phase lock states that occur throughout the phase diagram, sort of in terms of the coupling strength and the frequencies. Okay, so let me just wrap up by saying that sort of like full circle, that those phase locked states, they are kind of like simple classical regular states that you can get in the system. The pumping states, as it turns out, and not only them, they're more like the chaotic states. So if you look at the Wigner functions, for example, for one of those chaotic states, it looks very exotic, like psychedelic. But the regular states, the locking states, in fact, they are sort of as classical as you get. They're kind of like states at the bottoms of the wells. But yeah, there's quite a bit of theory that one can do here, which is quite fun. And this is just to finish off with this Poincaré map representation of the systems, that you can get like regular islands, you can get more chaotic behaviors, and all of that depending on the initial conditions that you set your system up into. So there is this interesting connection between the quantum and the classical systems that you get for these types of models. So to summarize, well, what I hope to have conveyed to you is that driven systems, they actually, okay, it's clear that they can be complex and interesting, but what I hope to have conveyed is that also they are fairly treatable. I mean, there's a lot of intuition that you can develop for them, and with that intuition, you can start building up, pretty interesting situations. So I showed you one example of how you can make topological insulator, but there have been quite a few interesting works for various energy pumps with multiple frequencies and so on that you can come up with, sort of taking advantage of those multiple extra time dimensions or mixing them also with spatial dimensions. And in fact, if you think about quasi-crystals, and that's a way to go beyond the sort of normal number of like spatial dimensions that we have access to. So like like Penrose tiles, they effectively 5-dimensional spatially. So you can imagine mixing high spatial dimensions with high temporal dimensions, and really the sky is the limit. So, but yeah, it's amenable to theoretical treatment. So it's pretty interesting, and there's some cool physics hiding in it. Yeah, thank you for your attention.
All right. Thanks for the very interesting talk. I can see that there were many things that we can explore that could be very interesting. I have several questions, but before I go, I want to ask, is there any question from the audience? You can just unmute yourself and ask questions. We can take several quick questions, and we can have the informal discussion unrecorded with Ivar. Any question? No. So then I go. So my first question is, so you have this analogy between your system, your driven system, and the topological insulator. So you will also have physical correspondence like the chiral propagating edge modes.
Yeah, there is something like this. Yeah, very good question. So let me. So actually, there are several answers to it. So okay, I'm sure there's a smarter way to flip through the slides, but I guess I'm sufficiently close. Yeah. Can catch this. Yeah. So you see that here, normally there is no boundary, right? If you have incommensurate drives, you just have this infinite N1 and N2 space. But the fact that you have electric fields sort of built into your system is kind of like the edge, right? Because I mean, what is edge? Edge is really just a confining potential which tries to keep your electrons in. So in a way, you have kind of like edge throughout the system. So that's one way to answer this question. But there is no effective separation between the edge states, and that is why you are not like super protected. So that's one way to interpret why the interband transitions can screw things up perhaps more easily. But having said that, I mean, there are ways actually to create something more like a real boundary in the frequency space. For instance, if you think of a real cavity, and then clearly n and that corresponds to the cavity cannot go into negatives, right? You cannot have negative number of photons in the cavity. So that's one thing. So the other thing which actually people have explored, so there's a paper by Gil Rafael and co-authors where they introduced a bit of a time delay in the Schrodinger equation, and they in fact they give a physical mechanism how this can be achieved geometrically by putting some loops and stuff. And it turns out that if you have if your Schrodinger equation effectively becomes like an integral or integral differential equation, then there's a way actually to introduce a kind of like a real boundary condition in the frequency space. And then you do get, or at least you can get edge modes within these kind of like strips of the frequency space. So yes, you can. I mean, that's certainly a possibility.
Okay, I think we're running actually a little late, but we can discuss my other two questions in the informal session. So with that, let's thank Ivar again for the really interesting talk. And if you're interested in joining us in the informal session, yeah, please, you can just stay.
Yeah, yeah. Thanks so much for your attention.
Yeah. Okay, just stop recording.
Mm-hmm.